Okay, we're going to now work a problem that's related to calculating buoyant forces. One thing that I want to mention, one critical thing, is always remember how to spell buoyant. It's actually B-U-O-Y. A lot of people try to spell it B-O-U-Y, but it's B-U-O-Y. So let's take a look at this example. And what we're going to do, this example is going to give us the opportunity to, in fact, calculate the buoyant forces on two things, on two objects. But let's take a look first at the statement of the problem. A metal part, object 2, is hanging by a thin cord from a floating wood block, object 1. The wood block has a specific gravity of 0.3. So it's significantly less dense than water and thus floats. And it has dimensions 50 millimeters by 50 millimeters by 10 millimeters. Note, however, that it's not completely submerged, that it's only that only 7.5 millimeters are below the surface of the water. This is going to be important when we calculate the buoyancy. The metal part has a volume of 6,600 cubic millimeters. So again, it's pretty small. And we want to find the mass of the metal part and the tension in the cord as part of this problem. And so let's go ahead and get a new page up. And so if we define the situation, we can see that we know that we have properties that we need to use. And so one of them is the gamma of water is going to equal 9810 Newton meter cubed, and this is coming from table 8.5 in the book, and we're given the gamma of the wood. We're given the specific gravity of the wood. So S is the S of the object 1 is equal to 0.3. And we're given the volume of the wood block. The volume of object 1 is 50 millimeters by 50 millimeters by 10 millimeters. We actually don't need that. We do need the submerged, the amount that's submerged, and we know that that is going to be this volume here. Because the buoyant force is equal to the weight of the water displaced, and so we need to calculate the amount, the volume of the object submerged. That's going to equal the volume of the water submerged. And so we also have the volume of the metal object as being 6,600 millimeters cubed. We can also see, and these are millimeters. Millimeters, 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 and this is a millimeter as well. So it's a pretty small box, small block with a small piece of metal hanging out. So the first thing to do is to draw a force diagram. So if we have the level of the water here, and the block is sitting in it, we've got a tension in the string, and then we've got this this object, which I'm just going to draw like this. We can draw a force diagram. Let me just use red for all the downward forces. So I'm not going to necessarily put these at their centers, but just to offset a little bit, this is going to be equal to what's pulling down on this is actually the weight of object 1 plus the tension in the string, and what's hanging down here is just the weight. The upward forces now on this, we're going to have an upward force on this, basically pushing in the bottom here, which is going to be the buoyant force on the first object. And the upward force on this object here is going to be equal to, if I write that over here, it's going to be the upward buoyant force on object 2, also plus the tension in the string. So we're going to use the force equilibrium on these to determine some characteristics of the, well, basically we want to find the mass of the hanging object, the metal object. So let's first apply force equilibrium to the box to find, or the block to find the tension. Right? So in order to do that, to find the tension is going to be equal, the tension of the string will be equal to the buoyant force on the first object, the wood block, minus its weight. And so the buoyant force is going to be equal to gamma times the volume of the of basically the submerged portion of 1, so S1, we'll call it S1, and then minus the weight, which will be, this will be the gamma of the water, and this gamma has to be the gamma of the wood. The total, the weight of the object will be the gamma of the wood times the volume, the total volume of the wood block, which is B1. That's going to be the tension. So if we write that out, we're going to have the gamma of water is 9810 newtons meter cubed, and the volume is going to be 50 millimeters times 50 millimeters times 7.5 millimeters. Again, that's just the submerged portion, and we're going to multiply that times a conversion factor to get the millimeters into newtons. This turns out to be 1 times 10 to the minus 9 meter cubed over millimeters, 1 millimeter cubed. Because you're basically taking the cube of 10 to the minus 3. So that's a small number. And if we can see that the canceling our units, the millimeters cubed are going to get canceled out, and the meters cubed are going to be canceled out, and what we're left with is just newtons. So the tension in the string is going to be in newtons, and multiplying, oh, I take that back. That's just for the buoyant force. We also have to subtract off the weight of the wood block, which is the gamma of the wood, which in this case is just 0.3. It's just going to be the specific gravity times the specific weight of water, Newton meter cubed, times the total volume of the block to give it the total weight. This is going to be times 50 millimeters, 10 millimeters, and again our conversion factor to get to newtons, or to get rid of the millimeters cubed, is going to be 1 times 10 to the minus 9th meter cubed over 1 millimeter cubed. And the units work out the same way. They're going to cancel out. The millimeters cubed is going to cancel all three of these, and this meter cubed is going to cancel that. So both these quantities, the buoyant force up top here and the weight of the block, are all in newtons. So our final tension will be in newtons. And if we calculate this out, we get 0.184 newtons for the tension in the string. Okay, take that back. That is the buoyant force minus this is the weight of the block. Not following my notes very well. The tension of the string is the subtraction of these two, which turns out to be 0.110 newtons. So that is the tension in the string. All right, so again, if we want to find if we want to find the mass of the block, let's just take a look at our final equation here. We have that the weight of the second object, the metal object, is equal to the tension in the string, which we now know, plus the buoyant force of the second object. So if we're looking to get the mass, of the object, we probably are going to focus on this guy right here because this is just m times g. It's the mass of the of the uh, of the metal object times g. We know what the tension is, and we need to find the buoyant force on the metal object. That's very simple to calculate. Again, remember I said in the other video for section 3.6 to concentrate on volumes, but we're given the volume. So the buoyant force on the second object is simply equal to the weight of the water displaced by that totally submerged fluid or object. So it's just going to be the gamma of the water times the volume of the second object. And so that is just merely 9810 Newton meter cubed. That's a cubed. And we know that this was 6,600 millimeters cubed, and we'll multiply that by our 1 times 10 to the minus 9 meter cubed per millimeter cubed, again, to get the units right. Units cancel in the same way. Like this, we're left with newtons. So the buoyant force on the metal object is just equal to 0.065 newtons. And so the final answer, well, almost, mg is going to equal the tension in the string, which we previously calculated to be 0.110 newtons. We're going to add to that the buoyant force, 0.065 newtons, and so mg equals 0.175 newtons, and the mass is now going to be equal to 0.175 newtons divided by 9.8 meters per second squared. 1 Newton equals 1 kilogram meter per second squared. And so we can then cancel these units. This cancels that, and this cancels that, and we're left, our final answer is left with, left in kilograms, which is exactly what we want. It's a reasonable unit. And we get, for mass, and we get, we get 0.0178 kilograms. And if we multiply that by 1,000 grams per 1 kilogram, these kilograms cancel. The final answer is in grams. Our mass of the object equals 7.8 grams. So the let's just recap that the important concepts for understanding this section really focuses on understanding what the buoyant forces are. So again, the forces that are pulling down on this are the weight of the object plus the tension in the string is pulling down as well. So those are the two forces that are acting on the wood block. But because the block is floating, it has a buoyant force due to the hydrostatic pressure distribution. It's pushing up from the bottom. That FB1 is balancing this W1 plus the tension. In addition, the force on the lower object is its weight, W2, but the upward force is equal to the buoyant force plus the tension in the string. So the tension's actually in the opposite direction. So the key to this problem was being able to calculate the buoyant forces, and that was extremely easy to do. It's just equal to basically the weight of the water displaced. That's gamma times the volume. If you remember that the force is, let me just get to a new, the force equals gamma times the volume. This gamma, if you remember, is just rho times g times v, but we know that rho is m over volume times g times v, and so gamma times volume is just equal to mg. So that's why we're calculating the force in the way that we are by using gamma times the volume, is because this really just equals m times g. So in both of these cases, we were both of the cases where we calculated the buoyant force, we were taking gamma times the volume of the submerged part of the object. So that's all I've got for this section. I hope this helps you understand the concept of buoyancy and how to use it in calculations of fluid statics.